Good evening, everyone, whoever is present. So, I will be starting now.
Good evening, sir.
Good evening, yes. All right. So, I'll be starting now. For people who are going to miss this tutorial, don't worry. The recorded session will be definitely posted on my YouTube channel. From there, you can go after and look at it after.
Sir, I want to ask you one question.
Yeah, go on.
Sir, these recorded lectures, will they remain forever on your YouTube channel or will they disappear
Yes,
after some time?
they will be remaining forever. Yes.
Okay, sir.
Yeah. All right, everyone. So, yeah. So, quick introductions before anything. So, this is Analog Circuits, and the instructor for this course is Dr. Jayanta Mukherjee. He is a professor in the Department of Electrical Engineering at IIT Bombay. My name is Mayank Anupam. I am a tutor for this course. I am a PhD student in the Department of Electrical Engineering at IIT Kanpur. Fine. So, okay, let's proceed now. So, before anything, let's do a quick recap. Now, by the way, today we'll be discussing the contents covered in week 3. All right. So, do you guys have any doubt in week 2? Those of you who are present today? I mean, I was not able to cover a lot of things, but I hope there was no doubt in week 2 as such. Uh, Tejasvi, please, could you mute yourself? Yeah, thank you. All right, so then we'll be proceeding with week 3. In
Sir,
this week, yeah,
sir, wait, I have one question. Let me just find it out.
all right.
Just give me some time.
Yeah, you find it, and then in the meanwhile, I'll be proceeding with the content that I have to cover today. Okay?
Okay, sir. Okay, sir.
Yeah, fine. So, uh, by the way, I just wanted to ask you guys, is 2 hours too long for you?
No, sir.
How about? Okay, okay, fine. No, because I was listening to my own tutorial and I felt like I mean I can bore myself, right? So 2 hours may be too long. If it is, just tell me, okay? I'll try to cut it short. Okay. I mean probably I'll finish it in 1 hour 30 minutes or 1 hour 45 minutes. If it is too much. Because we don't even have a break, right? So if it is too much, I'll just cut it short by half an hour. 1 hour 30 minutes is also good enough time to cover things which I want to cover. All right. So
Sir,
yeah,
sir, I have my question over here.
yeah, go on.
Sir, there is an op-amp with the
Hmm.
non-inverting terminal grounded.
Okay, let's do it. So this is a what digression, right? And basically, question is you have an op amp,
In which non-inverting terminal is grounded,
so non-inverting terminal is grounded. All right.
and from the input side there is one capacitor to the inverting terminal.
Is it like this?
Yes, sir, and its value is 0.01 microfarad,
Okay.
and there is a feedback of resistance is equal to 22 kilo ohm.
This is 22 kilo ohms. Okay,
Sir, and we are asked that input we are providing a square wave, then
okay.
what will be the output?
You tell me, what do you think should be the output? Don't you
Sir,
identify the circuit? Don't you know what the circuit is? It was covered
I
in
know
the lectures,
actually the
right?
circuit. Yes, sir.
What is this?
Sir, it's a differentiator.
Good. It's a differentiator.
So,
That's
but the
good.
confusion is the input, how we can judge its slope because it's
Good.
already zero at the
You see,
level.
okay. One second. I think I covered this in the last lectures. Okay, last lecture I covered this. Tell me something. If you have, okay, let's do this. If you have a ramp like this, what is the slope of this? A linear line like this, what is the slope of this line? I mean, this will be fixed, right? It will be some slope k, correct?
Yes, yes, sir.
So if you differentiate it, if you pass it through a differentiator, then what should happen? It should output a
Zero
simple
slope.
constant line, right? No,
Yes.
constant k, right? K scaled, probably scaled by some factor, right?
Okay.
But it,
Yes.
it will be a straight line. I mean, sorry, it will be a constant line, right?
Yes.
Good.
Yes.
Now, next thing I want to ask you, if you, let's say, if I start increasing the slope of this line, so how will this line start to become? I mean, by increasing the slope, what do I mean? Should I tilt it in this direction or should I tilt it in this direction if I want to increase the slope?
Yeah, we should tilt it in the anti-clockwise direction.
Anti-clockwise direction. Very good. So there will come a time. I mean, and you know that as this slope is increasing, the value of k will also increase, right?
Yes, sir.
Very good. Now tell me, I'll draw second line. Okay, just to, so if this is the line, okay, so its slope k dash will definitely be larger than k, right?
Yes, sir.
Okay, very good. Now proceeding in the same direction, if let's say in the limit of it, if I increase it to such a limit that it becomes something of this kind,
Okay.
okay, then what will be the slope of this line?
Infinite.
Infinite, right?
Yes.
This is the infinite slope, correct? Very good. Because tan theta, tan of 90 is infinite. Very good. Now, tell me that, okay, now that you know that it is infinite, tell me something. If this is a, this was the input, right? Let's say this was some zero value, or not zero, let's say it was some value, some constant, let's call it k, okay?
Yes.
Let's call it k. It was some constant k signal, okay? It was moving like this and it was going through a differentiator. So this is a differentiator, okay?
Yes.
And it was coming out. So tell me what will come out? Okay, probably this is not good. So this is your input. Let's call it x of t, okay? And this is your output y of t. Let's say x of t initially was like this, a simple uh, constant signal, okay? K. So what is going to come out of yt?
Constant signal.
No, it's a differentiator, right? A constant when differentiated is zero, right?
Yes, sir.
Yeah, basic zero.
Yeah, good. So it will be zero here, isn't it? Now tell me
Okay.
something. Let's say suddenly I make a jump of this kind. At this point, what is going to happen? If the signal jumps suddenly with a slope which is equal to 90 degree, which corresponds to a slope of 90 degree. So what is going to happen?
The output goes to infinite.
Yes, it does indeed go to infinite. Okay, it actually goes to infinity. Is that right,
Okay, sir.
Atar?
Yes. Yes.
Were you convinced? It should go to infinity, isn't it? It should immediately jump to infinity, shouldn't it? Right?
Yes, sir.
Or you are not convinced. Your tone doesn't look convincing. What is the problem, Athar?
Sir, uh, when we give a jump that way, right?
Okay,
So
one second.
it's
Uh, yeah, you proceed. You proceed. When you give a jump like this, yes. So
yes. So its slope is infinity, right?
yes.
Yes. So x plus c if we write its differentiation would give, sir. Basically, I'm not able to understand how we can differentiate that line, vertical line, sir.
What do you mean by differentiation? Okay, how do you differentiate this? Let's say instead of that vertical line, you have a line like this. Okay, after this constant period, it it did something of this kind. So what should be the signal here at the output after this zero?
Uh, Tan theta.
Tan of something, what, right? Tan of theta, right?
Okay, okay, I got, sir. I got, sir.
Right now, you got it, right? Good. All right. In but see, the thing is that uh, this is not a what? No, this will be actually infinity. There's no doubt in that. Okay,
Yes, sir.
so it's a differentiator. It
Yes,
should be infinity. It should do this. So basically, your output should do something of this kind.
yes,
Let
sir.
me take a different color. It will be zero. Okay, and then suddenly it will jump to infinity. Okay, and then suddenly it will come down also. So it will be like impulses. Okay,
Okay,
Im-
okay. Very sharp. Okay,
impulses like this. Okay,
okay, sir.
uh, fine. Good, good, very good.
Thank you, sir.
Yeah, yeah. All right.
Sir,
Yeah.
sir, what if the width of the impulse is more? The
What,
input impulse?
what input impulse? This one. I mean, this is not an impulse, right? This is a square wave.
Okay.
So, what do you mean by width of the impulse being more?
What I meant was, you told it'll go to infinity at one point.
Yeah, it will immediately go to infinity and then suddenly come down. Yes.
Yeah, but what it's a value k, it's coming, it jumps up and stays there for some minutes and again comes down the input.
I am not getting your point. Oh, one second, one second. I think I made a mistake. Let me do this. So it will be V in upon. Okay, let's do it together. Okay. So what is this? This is a differentiator, isn't it? So what does differentiator
Yes,
do? It does this. Oh, let's solve this. It will be much better. So if we have so this will be 0, right? This will be 0 here. So it will be C times whatever C this is. C times dV in upon dt. That should be equal to how much? This is the current, right? That should be equal to V out minus
Yes,
V out upon R, right?
yes, sir.
Correct?
yes,
Fine.
yes,
Let's do this. So basically V out should be what? Minus of RC times dV in upon dt, right?
yes.
Yeah, so what is the problem? I'm not understanding. It should suddenly jump and then it will not do that. What you're saying? Okay, so this will be actually like that only. When you find the slope or when you differentiate a unit step. So this is like a unit step, right? Isn't it? You
Yes,
have you
yes,
guys
yes, yes.
studied this in signals and system? When you differentiate a unit step, yes, you are going to get what? You're going to get an impulse, isn't it?
Yes, yes, got it, got it, got it.
Yeah. And the
Yeah.
other way is that when you integrate an impulse, you're going to get a unit step, isn't it?
Yes, yes, right, right.
Yeah, yeah, fine. Any other doubt? Anyone?
No, sir.
Very good. Yeah, good that you're asking questions. It it helps me also. All right. So let's. In week 3, was there a doubt in this part, first part, frequency response? I mean, these were the topics that was covered, right? That those were covered in the week 3 lectures. So was there a doubt in this topic, frequency response?
From my side, no, sir.
I mean,
No, sir.
No, sir.
okay. Thank you. You only say if you have a doubt, okay? Otherwise, you can keep quiet, okay? So I'll just ask, was there a doubt in this topic, poles and zeros in MOSFET, and basically Miller's theorem? So basically, there was a big circuit here. Probably it's
Yeah, I was about to ask that.
yeah. This was a big circuit, right? So was there a doubt in this?
Yes, sir. That midband gain, sir. How do we find that?
All right. Any other thing?
Same, sir.
Okay. Moving on. You see, by the way, that circuit that you just saw, it's not just for making your life difficult. Okay, this circuit has a very, this circuit is a very practical circuit. Okay, this is a equivalent, small signal equivalent of a MOSFET. Okay, so let's see what is this. There's nothing. Hmm. So this is basically a small signal equivalent of probably I will draw the circuit. It will make more sense. So you have this circuit, okay. Mm, RS, RG, and what else? Probably I will. Good. Then what do you have? You have this RL, CL, and CGS and CGD. These are parasitic capacitances. So now I will be drawing parasitic capacitances. Just to make it more clear, I will use different colors. So one of the parasitic capacitor is here. This is CGD, okay, gate to drain capacitance, and the other one is here. It's called CGS, gate to source capacitance. Okay, you will also have a capacitance. You can also have a capacitance at this point. In fact, you will have capacitance, some parasitic capacitance, say CDB or whatever. Let's call it CD, okay, drain capacitance. But that will be in general. You see that CD is coming in parallel to CL, right? So in general, we do not bother to mention CD, because whatever CD will be, it will be actually consumed in CL, okay? So when we do the analysis, if we have assumed CL, it's as good as saying that CD is also there, because CD and CL are in parallel. So that is why their equivalent capacitance will simply be CD plus CL. In general, CL is so large that it will be actually CD will be negligible compared to CL. Okay, so generally we don't bother to mention CD. Okay, so now that we know this, now the small signal model of this guy is this one. Okay, do you guys know something about small signal modeling?
Yes, sir.
No, sir.
You don't know? Okay. Oh, you have heard it for the first time, or you just don't remember it?
Sir, I'm hearing it for the first time.
That is not good.
Sir, I also.
Okay. Then probably this was not required from my side. This was not probably required. Probably you will. Okay. So basically, actually, this is going to be taught in week 7 or 8, I guess. Although this was not probably necessary. Okay. So just ignore in that case. Okay. Those people who know, it's for them that this is the small signal model. If you don't know, it's okay. Fine. Don't worry about it. Just don't beat yourself up. Fine. So in that case, we'll just focus on this guy. But those guys who don't know about small signal model, you know what is a controlled source, right? Voltage controlled source, current controlled source, all those sources.
Yes, sir.
Yes, sir.
Yes,
That
sir.
is good enough. That is good enough for me. That is good enough. So do you see any controlled source in this case in this figure?
Sir,
Yes, yes.
GMVGS.
Yes, very good. GMVGS. This is the control source. Fine. So now, did you guys understand the lecture when in the lectures I talked about about how to find out the about how to find out the poles and poles in the circuit? Did you guys understand that?
No, sir.
So
No, sir.
there were three methods given by sir, right? Can you just name the three methods?
First one is dominant pole method.
Okay, let's also mention write it. So okay, methods to find the poles in the circuit. Okay, what were they? First
Dominant
was
pole method.
dominant pole method. Okay, go on.
Using Miller's theorem.
Using Miller's theorem.
And the next one is the rigorous one using KCL and KVL.
Yes, very good. Okay, so I don't think you have any doubt in this, right? This is plain and simple. You have to apply KCL and KVL.
No,
Did
sir.
you guys understood this, right? Rigorous method.
Yes. Yes, yes.
Okay. Probably you had some doubt in dominant pole method.
Yes, sir.
Hmm. You see, dominant pole method comes from the. I mean, this is an approximation. Okay, it is not an I is not the this thing. It's not very accurate. I mean, sorry, it can become close to, its accuracy can be close to perfect if certain conditions are met. Okay, that is why it's called dominant pole method. Only when you have a dominant pole in the circuit, this will be very close to an accurate answer. Okay, however, if you want a really accurate answer, perfect answer, you have to go through this rigorous method. Okay, this gives correct answer, very perfect answer. Fine. Dominant pole method works when you have a dominant pole in the system. Now the idea behind its working is just not for you right now. Okay, it's not required for you to know right now. Only thing that you need to know is if you have a dominant pole in the system, and I'm talking about the poles which are going to be high frequency poles. Okay, so I'm talking about this particular scenario where let's say your your response is probably
सर
of this. Yeah.
समझ में नहीं आ रहा है सर, फिर से एक बार एक्सप्लेन।
नहीं नहीं, अभी समझाना शुरू नहीं किया है, अभी समझा रहे हैं.
ओके।
Okay. हाँ. Dominant pole method is going to be helpful only when you have a dominant pole in the system. Okay. So this is gives close to accurate answer or accurate pole rather, when there is one dominant pole. If you don't have a dominant pole, and what do I mean by dominant pole? You see, in the response of this kind, this is what? This is a low pass kind of response. When someone asks you what kind of a response is this, you have to say this is a low pass response. Okay. Why do you say this is a low pass response? Because lower frequencies are going to be passed, right? Because they see a gain, a large gain, right? They see probably a gain of maybe 0 dB or 10 dB, whatever, but it is larger, right? But higher frequencies, on the other hand, they are going to be attenuated, isn't it? When I draw this, this is a magnitude plot. Okay, this is a magnitude plot, Bode plot of magnitude, right? So in this kind of a response, this is a low pass response. On the contrary, what kind of a response is this? I mean, you guys should probably guess also. What do you think of this kind of a response? What kind of a response is this?
High pass response.
Very good, high pass response. Very good. So in that case, you know what is the next question I'm going to ask? What is this response?
Band pass.
Yes,
Band.
this is
Band
band
pass.
pass. Very good. So this is low pass. This is high pass, and this is band pass. Very good. So now that we are clear on this, whatever I'm going to talk about right now, dominant pole method is applicable for high frequency poles, and so yeah, so this is going to be applicable for low pass response as well as for band pass response. Okay, and this is going to be applicable for high frequency poles. Okay, not the low frequency poles. So in the band pass response, we have two kind of poles, right? One which comes in this side and the other one which comes in this side, isn't it? Right.
Yes.
So I'm talking about this side of poles. Okay, in this case also this side of poles. So in low pass response, there is no confusion because there is only one side where you can get poles, but in band pass you might have some confusion. So that is why I just thought to mention this. Now when you have a low pass response and you have multiple poles in a low pass response, let's say you have a lot of poles, let's say you have n number of poles. Okay, let's say you have n poles, and let's say the poles are something of this kind. Okay, so in this case you can clearly see in the way I have drawn it, this pole comes very earlier, right? This pole comes very early, isn't it? Whereas all the other poles here, they are far away from the first pole, isn't it?
Yes.
Yeah, so in this case we call this pole here as a dominant pole. Okay, we call this pole as dominant pole. We call this pole as dominant pole. Now why do we call this pole as dominant pole? The idea is that when you have a low pass response, okay, and the poles are going to be high frequencies, what is the purpose of this pole here? What do you think is the purpose of this pole? What is the purpose of this pole? What happens when this pole comes into effect? Anyone? in the magnitude response, when a pole is hit at a certain frequency, what is going to happen to the magnitude after that?
It decreases by
It
22
starts to decrease.
kilometer.
It starts to decrease. Very good. It starts to decrease. Yes. Now tell me something. Uh, now can you guess why do we call this pole as? Oh, sorry. Why do we call this pole, the first one here, as a dominant pole and not all the others?
Yes,
Why do you think?
because after that it starts to fall.
It starts to fall. Very good. Now, if this pole is much farther away, all the poles are much farther away from the first pole, it doesn't matter where they hit or not, right? The magnitude is already so small that there exist all these poles, whether they exist or not, doesn't matter, right?
Yes.
Do you
Yes,
understand my point, everyone? Yeah. So that is
Yes.
why the first this pole here, it's called a dominant pole, because it is much farther away from the other poles, and its existence is good enough to dominate the overall response of the circuit. Okay, this guy here, its existence dominates the overall response. Okay, now if you are familiar with the time domain, this thing time domain this time domain uh, 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 basically what does this translate to, the what does the pole translate to in time domain? Do you guys remember that? What happens due to a pole in time domain? So poles and zeros are frequency domain nomenclature, right? What
yes,
happens to how does a pole translate in the time domain? Anyone?
an exponential.
Very good. It's actually an exponential. Yes, yes, you're good. So let's say you have a pole P1, okay, in a circuit. So due to this, you are probably going to see an exponential a response of this kind. Is some factor here a naught times exponential of minus t into p1. Okay, this is going to be the response that this is going to be the response that you see. Okay, and by the way, this
Yes, sir.
p1 is sorry, this is minus p1. Okay, this is minus p1. Okay, it's a left hand side pole,
Yes, sir.
left half plane pole. Okay,
Sir, basically,
basically
sir,
what?
basically we can understand that when a pole occurs, gain,
Huh?
gain increases to a very large magnitude. That's why it is exponential,
No, no, no,
right?
no, 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 not that. No, 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 that you are confusing the two things. This is Laplace transform. Okay. Uh, sorry, this is what? This is Bode plot is a Bode plot is what?
It is in the Laplace frequency
Uh,
domain.
frequency domain, right? When you convert
Yes.
it into time domain from Laplace domain, sorry, or frequency domain, when you convert it back to time domain, the pole gets converted into an exponential. Okay, that's how it is.
Okay.
That comes from maths. Okay.
Okay.
Yeah. So this is coming from math that it will be of this kind, something of this kind. Okay. Now, if the p value is small, okay, and all the others also. Let's say you have p through p3, p4, all those. So this will be a1 times. Also, let's call this p0. A1 times exponential of minus t p1. Okay, and plus a2 times exponential of minus t p2, and so on. Okay, like this only. Now let's say your p0 is much smaller than all the other. So what is going to happen? So this now I'm taking you back to your 12th class. Okay, so forgive me for that, but this is a very important thing. This is generally missed by almost everyone. This kind of confusion remains for a lot of students, so that is why I thought maybe I should spend some time on this. So if now I'm talking about time domain. Okay, and so what is, let's say if the first one which is a0 times a naught times exponential minus t p0 if its curve looks something of this kind. So this will be like this, right? The first one, isn't it?
Yes, sir.
Yeah. So what should be the second one? How should the second one look like if this relation holds? P0 is much less than P1, P2, P3 and all, Pn. So how should be the curve? How should the other curves look like?
All of them very quickly fall to zero.
Very good.
Yes.
This will be like this, right? Something of this kind. I mean, all the other ones, they will be probably like this, right? And
Yes,
so
sir.
on,
Exponentially
isn't it?
decreasing, sir.
Yeah, very good. They will all exponentially decay. However, the rate of decay for this guy, which is corresponding to p0, will be much slower compared to the rate of decay for all the other guys, right? Isn't
Yes,
it?
sir.
Very good. Now, can you say and you see that at any time, the overall response, let's call it v0, or let's call it v0. Okay, v0 is the summation of all of this at any time. Okay, so tell me which uh, after a very long period of time, after a long period of time, which of these terms, which of all these terms is going to dominate after a very long time in
First one, sir.
v0? Very good.
The P0.
Yes, exactly. This will be p0 because after a while, all the others have gone to 0, right? Only this guy remains. So the summation of all of these will simply be dominated by the first one, isn't it? So this is also one way to understand why p0 is called the dominant pole. Okay.
Yes.
So these are different ways to look at the same thing. In the frequency domain, p0 is called dominant pole because after this, doesn't matter if any other pole hits also. If it is much farther away, if all the poles are much farther away, this is going to do the job, isn't it? This is going to take the game. And in the time domain, a similar thing can be said. Okay, fine. So yeah, I was talking about dominant poles, right? Dominant pole method. So when you have such a system where you have one dominant pole and the other are non-dominant poles, and the condition for dominant poles was, I mean, for a 202 pole system was told to you, right? If it is 4 times lesser, then it can be considered as a dominant pole, right? That was told to you in the
Yes.
lectures. Yes. So if that condition holds, then you can say that the overall time constant of the circuit is going to be dominated by this particular guy here. The overall dominant pole is going to dominate the overall system, and this is going to be the dominant pole. Okay, and how do you find that dominant pole? You find it by doing this summation of 1 over summation of Ri times Ci, isn't it?
Yes.
This is the pole. And what is Ci and Ri? Ci is basically all the independent capacitors which you see in this circuit. So how many independent capacitors are there in this circuit? 1, 2, 3, right?
Right.
Yes, sir.
Yes.
Yeah. And what are the hmm, 1 second. Yeah. And what are RIs here? What are they?
Resistance across the capacitors when all the others are shorted.
Yeah, good point. Now that you said that, why do you say it's shorted? Why do you short it?
Sir, basically, I too didn't understood that point, sir. Why did we short them?
So this is actually not going to be covered in the lectures, and yeah, Ganesh, I'm coming to that. You have asked that. Could you please explain the part of finding the Ri? Okay, I'll be coming to that. Okay, but right now the thing is that why do we find Ri in the manner that we do? Okay, we basically short Yashwant, you have a doubt? You raised your hands.
So capacitor should be open, right? Not uh,
Oh, sorry. Yeah, I mean, yeah. Good point. Sorry, I was taken by the flow. For finding the high frequency poles, yes, they should be opened, and for finding the very low frequency poles, they should be shorted. Yes. Thank you for pointing it out. Yeah. So, but why do we open it?
because of the superposition theorem, the effect of uh,
Yeah, you are on the. I mean, you're close. Try.
the resistance. The Ri will be the resistance offered by all the capacitors. So we are opening. We are considering one capacitor and we are opening a rest other and finding the effect of it.
Yeah, but why do we open it? Why don't we short it here also? Why do we
Sir,
short at
basically,
one place and open at one place? Why?
basically we need to consider the reactance of the capacitor.
Yes, I mean, not reactance. I mean, you have to consider we are trying to find out what is the equivalent resistance, right, across the capacitor, because that is how we find out the time constant, right? But I want to know why do we short it here? And for finding the low frequency poles, why do we open it? Sorry, the other way around. Why do we open it here for finding the equivalent resistance in the high frequency case, and why do we short it for finding the equivalent resistance in the low frequency case? Why do we do it opposite? I mean, why don't we short at both places, and why do we not open at both places?
Sir, 1 by 2 pi fc by that formula, if we put the low frequency over there, then in one case the resistance will become 0, and the other case it will become infinite, sir. That is basically short and open case.
Yes, exactly. So see, the thing is that it is very logical. Okay, it is very logical. You see, you have to consider the effect of one capacitor at a time, right? You are assuming that you are going to assume while finding this that only one capacitor is there and all the other capacitors are not in the picture, and they are not going to be affect. You always take in this case as while finding it out RICI, what you do is you assume that there is only one capacitor that is dominant, the other capacitors are non-dominant. Okay, now what does dominance and non-dominance mean in the case of high frequency case? I mean, what did I just talk right now? I said that in the high frequency case, you see, once a pole hits, okay, once a pole hits, what happens? The magnitude starts to drop, right? Isn't it? So, we know that the classic example, an RC circuit here. If this is an RC circuit, we know that this has a pole, right, at the output. I mean, this has one pole which is given by 1 over RC, right? This has one pole at 1 over RC, right? This is a classic
Yes.
RC circuit. Now what happens when this pole hits? The capacitive this thing impedance starts to drop, right? A lot. I mean, the capacitive impedance always drops, but after this frequency, what happens? Its drop is really going to be dominant, isn't it? And in the I mean, if you are going to push the limit, you can say that you can even say that after this frequency, after 1 over RC, this capacitance is as good as a short circuit. I mean, I'm just stretching it very far, but you can make a comment like that, isn't it?
Yes, sir.
Yeah. So that is why when you are trying to find out uh, um, high frequency poles, okay, when you're trying to do this RICI, okay, and you're trying to find out which pole is you're trying to find out the individual effects, okay, assuming that the effect of all the others are not there at all. So what does that mean in high frequency case? It means that all the other poles have not hit till now, right? I mean, all the other
Yes.
capacitance are not present in till now, are not showing their effect till now while moving in the high frequency direction, okay. And in the high frequency case, if the other capacitance have not shown their effect, it means what? They are simply not there, right?
Yes, sir.
Whereas in the low frequency case,
नोट
if
लास्ट
हाँ
वाला कंसेप्ट अंडरस्टैंड में नहीं है, फिर से एक बार रिपीट।
हाँ अच्छा ठीक है।
हाई
देखिए
फ्रीक्वेंसी वाला।
हाँ 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 बता रहे हैं। हाई फ्रीक्वेंसी के केस में क्या होता है, इसका काम क्या है, हाई फ्रीक्वेंसी पे अगर कोई पोल या कैपेसिटर आता है, ठीक है, हाई फ्रीक्वेंसी सिग्नल को कैपेसिटर क्या करेगा, उसके साथ कैपेसिटर क्या करता है, उसको कैपेसिटर से बहुत छोटा सा इंपीडेंस दिखेगा, राइट, क्योंकि कैपेसिटेंस
यस
का
सर।
इंपीडेंस क्या होता है, 1/2 पाई
टू
एफ
पाई एफ
सी,
सी।
राइट। हाँ, तो जैसे जैसे फ्रीक्वेंसी बढ़ती जाएगी कैपेसिटेंस का इंपीडेंस घटता जाएगा, है ना।
यस सर।
हाँ वेरी गुड। तो आप मेरे को बात बताइए, हम आपसे ये पूछना चाह, इस स्टेटमेंट, ये जो फॉर्मूला लिखा हुआ है यहाँ पे, इसका क्या मतलब है, इसका मतलब है कि हर एक कैपेसिटर को एक एक पकड़ना है ना, और उसके क्रॉस रेजिस्टेंस
यस।
फाइंड आउट करना है, ठीक है।
यस सर।
हर एक कैपेसिटेंस को ऐसा अज्यूम करना है कि सिर्फ अभी वही है, बाकी किसी का इफेक्ट नहीं आया अभी तक, बाकी किसी
यस सर।
कैपेसिटेंस का इफेक्ट नहीं आया है, उस फ्रीक्वेंसी पे बाकी किसी कैपेसिटेंस का इफेक्ट नहीं दिख रहा है, राइट,
यस सर।
करेक्ट। हाँ, तो जब ऐसा हाई फ्रीक्वेंसी के केस में बात होती है ऐसी बात, तो इसका मतलब ये होता है कि आ, अगर हाई फ्रीक्वेंसी पे किसी कैपेसिटेंस का इफेक्ट नहीं दिख रहा है, इसका मतलब क्या हुआ कि सिग्नल को कैपेसिटेंस जो है अभी भी तंग नहीं कर रहा है, राइट, उसको परेशान नहीं कर रहा है, सिग्नल कैपेसिटेंस के थ्रू बहुत ज्यादा अटेनुएट नहीं हो रहा है, राइट। और कैपेसिटेंस के ऊपर कोई सिग्नल आएगा, कोई वोल्टेज सिग्नल आएगा, तो क्या होगा आप बताइए मेरे को। जैसे इस केस में अगर कैपेसिटेंस का इफेक्ट डोमिनेट करने लग जाता है पोल के बाद, राइट, इस केस में कैपेसिटेंस का इफेक्ट जब डोमिनेट करने लगता है पोल हिट होने के बाद, तो क्या होता है, यहाँ पे जो भी वोल्टेज होता है वो गिरने लगता है, राइट, ऐसे गिरने लग
यस
जाता है
सर।
नीचे,
यस।
है ना। लेकिन अगर वही हम बोल रहे हैं आपको कि अगर हाई फ्रीक्वेंसी पे किसी कैपेसिटेंस का इफेक्ट नहीं दिख रहा है, इसका मतलब क्या होता है कि उस कैपेसिटेंस की वजह से कोई प्रॉब्लम नहीं आ रही है, अभी अभी सिग्नल अटेनुएट नहीं हो रहा है उस कैपेसिटेंस की वजह से, है ना।
सीधा ग्राउंड हो जाएगी। हाँ मीन्स क्या, हाँ।
तो इसका मतलब ये होता है ना कि आप उस कैपेसिटेंस को बोल सकते हैं कि उस कैपेसिटेंस की जरूरत भी नहीं है यहाँ पे, राइट। अगर जैसे कि मान लिया जाए कि सीजीडी के बारे में देख रहे हैं सिर्फ, कि सिर्फ सीजीडी इफेक्ट कर रहा है, तो उस केस में क्या मानेंगे हम लोग कि बाकी सारे कैपेसिटेंस जो है वो पिक्चर में ही नहीं है, वो तंग ही नहीं कर रहे हैं, वो सिग्नल को परेशान नहीं कर रहे हैं, मतलब वो सिग्नल
यस
को
सर।
जरा सा भी अटेनुएट नहीं कर रहे हैं, करेक्ट।
यस सर।
हाँ, तो यही समझाना चाह रहे थे हमको। जबकि लो फ्रीक्वेंसी के पोल्स को फाइंड आउट करते वक्त जब हम लोग बोलते हैं कि उस वक्त कोई कैपेसिटर परेशान नहीं कर रहा है, इसका मतलब ये होता है कि वो कैपेसिटेंस जो है वो सिग्नल को पूरा पूरा पास होने दे रहा है। इस केस में वहां पे शॉर्ट करते हैं, यहाँ पे ओपन करते हैं। इफ यू आर नॉट अंडरस्टैंडिंग दिस एट द टाइम, it's okay, I mean, give it some time, it will sink in later. Whatever I just said today, you can go back and think about it, you will also get it
ओके।
anyway.
Sir,
Yeah. Yes.
so this means for high frequency, the across which we are finding the resistor, we need to short that and open the others, right?
Come again, for high frequency.
For high frequency, the capacitor across which we are finding the equivalent resistor for that formula, we
Uh-huh.
have to from this impedance as it gets low, we have to short the capacitance and open
No,
all the other ones, right?
no, 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 you don't have to short anything. uh it is just like finding Thevenin's resistance across a capacitance. You just have to remove this capacitance from the, let's say you are trying to find out, okay, let's do it, okay, let's do one once. Huh, let's try to find out. So we have, let's first do what, let's first do CGS, it's the easiest, right, or CL, whatever. Let's do CGS. Okay, let's do CGS. Yes. So what is going to be the value? I mean, how do we find out? How do we do? Tell me. What do we
We'll
do?
open CGD.
We'll open CGD. Very good. We will open CGD. We will open CL. Right?
Yes.
And what do
Yes.
we do next? So, okay, step by step.
We'll
So,
short the input.
one second. Finding the overall circuit's time constant. Oh, by the way, this method is called open circuit time constant method. Open circuit time constant method. If you want, you can look at it in any standard book. It will be there. Okay. Yeah. So first thing is, op for what is the open circuit time constant? Tau is given by Ri summation Ri Ci, right? Ri Ci. So what is uh, so this will be, or rather, this is fine. This will be R1 or R, probably let's write RGS times CGS, okay, plus R GD times CGD plus RL times CL. Oh, this is there is a conflict here, so I will simply denote it as R load into CL, okay, because RL and R load are different, okay, fine. Now let's do it. So finding RIs. So first thing, in the first step, let's find out RGS. So how do we find out RGS? As one of you pointed out, first we have to open CGD, right? Open
Yes.
CGD and CL, correct? Very good. After that,
We'll short the input, sir.
we will
V.
short the input. Very good. So then we will short the input. This is 1, this is 2. Short the independent voltage sources. Had it been a current source here, what should you do?
Open.
Yes,
Open.
and open all the independent. I mean, this I am stressing this word independent because we are not shorting or opening this, right? GM times VGS. This one is not affected. This we are not going to touch. We are only going to short or open independent sources. Okay. Yeah. So independent current source. Fine. What else? So this is sorted. Okay, I will short it later. Fine. What else? Anything else?
Nothing, sir.
Nothing. I have to find RGS.
Yes, RGS, like it's parallel.
What parallel?
RS. RS parallel to
Okay,
RG.
let's draw the circuit first. Okay. So it is, here is RG. Okay. And this is shorted, right? So this is grounded. And this is RS. No, this is RS, right? This is RG. And then we have this capacitance here, which is CGS. Then we have an open, right? There is nothing. And then we have GM times VGS. And where is VGS? This is VGS, right? We have CL and then, oh, so we don't have a CL, we only have RL. Yes, so now how do we find out this thing? RG, RGS. What is RGS?
Resistance across CGS.
Resistance
Equivalent
across CGS, right? The equivalent resistance across CGS, isn't it? So how do you
yes.
find equivalent resistance across anything? You first remove that element altogether, right? If you have to find out equivalent, no, sorry, that might be actually that cannot be generalized. That statement cannot be generalized. So how do you find equivalent resistance across this capacitors? First you have to remove the capacitance, okay? First you have to remove the capacitance here. Could you give me a minute? Yeah, sorry for that. Where was I? How do you, yeah, in this case, how do you find the equivalent resistance? You find it by first opening the capacitance here, and then you have to find out what is the equivalent resistance. Okay, so if you do that, what will you find out?
Sir, we can
RSRG
immediately.
parallel.
Yes, exactly. So in this case, R equivalent, or which is simply equal to RGS, okay, will be RG parallel RS, right? That is
Yes,
fine.
sir.
Very good. Now let's do the other easy one, the second one that is easy, which is R load. How do you find R load?
Again, short CGS and CGD. Open, sorry.
Yeah, again open CGD and CGS, right?
CGS.
So these two are going to open now. Sorry, these two are going to be open now, right? Very good. So let's do that. So there is a, this is sorted. There is RG here, no sorry, RS here. This is RG here, and then we have what? We have to open this capacitance, so this is not there, and the second one also we have to open. So this is opened here, and this is VGS, GM times VGS times RL. Hmm. And then Cl. Yeah. Now how do we find out? Again the same thing, right? We have to find out the equivalent resistance across these 2 points. Correct? So what is it?
Yes.
What is it? What is the equivalent resistance now? Okay. Tell me something. What will be VGS? What should be VGS?
No idea.
So maybe 0 because we don't have any input.
I mean, yeah, of why not? I mean, it should be right because you see there is no input here. From where will VGS be non-zero? I mean, for VGS to be non-zero, there should be some current, right? Where will the current be coming from here? Isn't it? It should be zero. VGS is actually equal to zero. Okay. So if VGS is zero, then what is this current?
0.
Very good. This is also zero. Gone. So what is the equivalent resistance now?
RL.
RL.
Very good. So what is R load? R load is equal to simply RL, right? Very good. Now let's come to the most, the tricky one. RGD. Okay. What is RGD? How do we find out RGD? So again, tell me quickly, what will be the equivalent circuit now? I mean, what will be the circuit? What things should be kept and what should be removed?
The open CGS, CL,
And keep CGS out.
short,
Short
op,
V in, right?
short the vein.
Yes. So let's do now. So we have again the same thing. This is RS here. And we have RG here. And then we have CGD here. GM times VGS. And this is what? VGS. We have RL. Yes. Now, where should be the, I mean, we have to find out the equivalent resistance here, right? How do we do that?
RS parallel RG plus,
Once
sorry,
again,
RS
don't tell me the
parallel
answer.
RG
Don't tell
plus
me the
RL.
answer. आंसर नहीं बोलना है, तरीका बोलना है. So we have to do
RS
this,
और
right?
RG पैरेलल में होगा और VGS 0 हो जाएगा तो वो वाला
अच्छा, okay.
0 हो जाएगा तो
Okay.
RL बचा तो RL सीरीज में उसके साथ.
Okay, let's do it. So we have this circuit here, okay? And then what else? RL
So
here.
GM VGS would be 0 over here.
Why? Why is GM 0 again?
So because we have shorted the input.
We have shorted the input, but now uh, we have to find out R equivalent between these two terminals, isn't it? How do you find the equivalent resistance between two terminals? What do you do?
Remove that.
You apply a
Connect to
voltage
one
source,
level.
Voltage.
isn't it? Voltage or current, whatever you want to apply, a voltage of V test, and you find out what is the current leaving the positive terminal, right? I test.
Yes.
Does this ring a bell?
Yes.
Yeah, good. So, okay, let's do it now. What will happen? Tell me.
Let's say V test is equal to 1 volt.
Let's call this terminal as V1. Okay, let's call this terminal as V2. So first of all, what is V1 minus V2? V test, right?
We test.
Very good. Equation number 1. What is V1 equal to? I test times?
RG into RG parallel RS.
Yes.
Yes. Fine. This is equation number 2. Alright. Now, similarly, what is V2? No, no, not like this.
GMVGS.
One second. What is again another equation of KCL at this node? Which node? At this node. What will be the KCL equation? I test is equal to what?
GM
GM
VGS.
times,
Which is
no, no, I test equal to what I am asking. The direction of I test is in this direction. Okay. What
Current
is
through RL
KCL?
minus GMVGS.
Okay, write KCL at this node. This current is like this. All the three currents are leaving this node, right? So I test
Yes.
plus GM times VGS, which is VGS is what? V1, right? V1 plus V2 by RL is equal to what? 0, right?
yes, sir.
So now replace I test with, no, sorry, replace V1 with,
सर
or
ये
rather
वाली
replace,
सर्किट से एक बार फिर से एक्सप्लेन करके ना समझ में नहीं आ रहा है V1
इसमें,
माइनस V2 वाला
ओ, ये एक पहला इक्वेशन समझ नहीं आया आपको, ये वाला.
नहीं ये समझ में तो आ गया उसके बाद
अच्छा, सेकंड वाला इक्वेशन,
यस
ये आपको समझ नहीं आ रहा है क्या? ओके, सेकंड इक्वेशन में ये लिखा हुआ है, इक्वेशन इस नोट पे लिखा गया है, आई टेस्ट करंट
ओके
जो
सर
है,
डन सर
समझ
सर
आ
हो
गया?
गया
हाँ, ठीक है, ठीक है, ओके.
हाँ
Okay, now let's replace I test. I test will be replaced by what? Here, I test can be replaced by using the second equation, right? By V1 by RS parallel RG. Okay, plus GM times V1 equal to minus V2 by RL, right?
Yes, sir.
Yes, and so you know now that what is V2 in terms of V1? It is RL divided by RS parallel RG plus, or rather it is 1 by 1 plus GM into V1 times RL minus, right? This is equation number third. Now if we replace our value of V2 in the first equation, if we do this, what is going to happen? It should be V1 minus V2 is what? Plus of V1 times RL into GM plus 1 over RS parallel RG, right? Yes, and equal to what? V test. Now if we replace V1 with I test into RS parallel RG, then what do we get? V1, if it is replaced by I test into RS parallel RG plus RL times GM times RS parallel RG. Is it correct, by the way, what I'm doing right now? If there is a calculation mistake, just point it out. Okay.
Yes, sir.
Plus what else? It is just RL, right? Isn't it? So what is B test by I test? RS parallel RG, okay, plus GM times RL, or it can be written in this manner, 1 plus GM times RL RS parallel RG plus RL, right? Isn't it?
सर ये V1 प्लस V1 इंटू RL उसके बाद ये सेकंड नंबर का लास्ट है सेकंड
ये
हाँ ये वाला इक्वेशन
हाँ, इसमें क्या दिक्कत है?
आगे आगे आई से कौन सा इक्विवेलेंट इक्वेशन पुट किया
अच्छा, ये वाला, ये वाला इक्वेशन डाला यहाँ पे. V1 is
ओके
replaced with I test into RS parallel RG. I mean, is everyone comfortable with the derivation here? I mean, is the derivation correct, by the way? Is the final
Yes.
answer correct? Is this RGD is equal to this one? Is it correct here? Is it correct?
सर एक बार एक्सप्लेन करिए ना वो वाला इक्वेशन को
Yes,
पीवी
sir.
का
Which equation?
वो लास्ट है सेकंड वाला
ये वाला.
यस सर
ये कुछ नहीं है, ये वाला इक्वेशन जो है ना, इसमें बस V1 को I test into इस वाले इससे रिप्लेस किया है बस.
ओके सर गुड
Yeah. Okay. Fine. So this is the equation for RGD. Here. So what is the final this thing? This is basically your R equivalent or RGD. Okay. So what is the final time constant? What is the overall time constant?
Summation of some all
Summation of,
resistors in R into C.
yes. So it
आ
is
रहा है इंटू
basically, so it is RL times CL plus
RG पैरेलल टू
GD
RS
times
GTS
CGD.
R. First, let's do the first one. So RS parallel RG times
CGS.
CGS plus what
R
is
test
RGD?
into
RGD is
It's
what? RL plus RS parallel RG into 1 plus GMRL times CGD, isn't it?
yes, sir.
Right? Is this correct?
Right, sir.
Hmm. Yeah, fine. So, I mean, this is how you find it out. This is how you find. I mean, a lot of people had the doubt in this question, right? I mean, in this, this was probably not clear to everyone. So now is it clear how to find out equivalent time and everything,
यस सर
equivalent
Yes.
वीक
resistance
थ्री
and everything?
वीक थ्री
Sir,
के असाइनमेंट
mid-band
में सेम
game.
क्वेश्चन है यस सर
1 second, संकेत क्या बोल रहे हैं आप?
वीक थ्री के असाइनमेंट में सेम क्वेश्चन है सर
अच्छा, ठीक है, तो अब समझ में आ गया ना आपको क्या करना है?
Yes, sir.
हाँ, ठीक है। या वसंती, मिड बैंड गेन इज नथिंग बट, you see, as I explained on that day, okay, the last class, last tutorial, mid band gain is nothing but the, I mean, if you're talking about a band pass response, okay, which is like this. Yeah, my figure is not good. What the? If it is like this, okay, then mid band gain is basically the second central portion with this one. Okay, the gain at this point. Do you get it now?
Sir, but how will we find it?
Oh, how do you find out?
Sir, any special formula or like method to?
Okay. So in if it is a band pass response, then basically you have to find out the mid band gain when the gain is maximum. Okay, that is the mid band gain. There is no formula as such. I mean, you have to understand what is meant by mid band gain. If you understand that, you'll be able to find out the maximum gain that you can get in a response. That is what is meant by mid band gain. This is mid band gain. Okay. This is too small. Hmm. And in a low pass response, the mid band gain is this one. So this guy here is mid band gain. Okay. Now, if you have a low pass response, then it is fairly easy to find the mid band gain, right? How do you find the mid band gain in this case?
Making S is equal to 0.
Yes. Basically, mid band gain here is equal to the DC gain, right?
Yes.
Yeah. So here, if you put S is equal to 0 in the Laplace transform, I mean, whatever this thing you are given, whatever response frequency sorry, whatever transfer function you are given, in that if you put S is equal to 0, you will definitely find out what is the mid band gain in a low pass response. But in band pass response, such a strategy won't work, right? So what do you do here? Yes, Vasanti, what do you think we should do here? Are you there, Vasanti? You asked this question to me. Oh, it looks like she's not there. Yeah, so other guys, what do you think we should do here to find out the mid band gain? S is equal to 0 clearly won't work, right? What should we do? What should we do?
Sir, bandwidth product.
You see,
Approximately.
in this case, what you have to do is we cannot find out by putting S is equal to 0. We have to first find out uh, after what frequency do we get this midband kind of response here. Okay, you first have to plot the Bode plot probably, and then you have to find out where you are getting this maximum gain. Okay, and then probably you have to put the value of frequency somewhere in the middle. Okay, where you are indeed getting the maximum gain, and when you do that, when you evaluate that, that is how you will find out midband gain if you have a band pass response. Okay.
Sir,
Huh?
can we use the bandwidth product concept?
Gain bandwidth product.
Yes, yes,
Oh,
yes.
that is actually only valid when you have only single pole system. Okay.
Okay,
I mean, not for band pass response, but even in band pass response, you can only have one low pole and one high pole. That's all. That's it. No more than that. Only then it is possible to find out. If you have multiple poles and multiple
okay,
zeros in the system, then that is a very crude approximation. That is not going to help you.
okay, sir.
Can't we
Yeah.
apply the cutoff frequency finding out and then
Yeah, that is what I said now here. You have to first find out what is the cutoff frequency. Okay. That's what. First find out what is the cutoff frequency. After what frequency this indeed becomes flat, and then you have to find out. Okay. So this is about mid-band gain. Now what else?
but if we don't know what type of circuit it is, then how can we find out?
No, no, you have. It doesn't matter what kind of a circuit is this. You first draw the Bode plot. From the Bode plot, you can see where the how is the response, where it is going to peak. Okay,
Okay.
and from there you find out what is the maximum this thing. What is the midband gain? All right, so I
Sir,
guess
I have a doubt in that previous example, sir. Sir, while finding resistor across CL,
I cannot
the
hear you properly.
is
Your
zero.
voice is cracking.
Now you can you hear me, sir?
Yes, yes. Now I can hear you. Yes,
Sir, while finding resistance across CL, we did take GMVGs to be zero, right?
across CL. Yes,
Yes, sir.
yes.
Yes,
So
sir. Sir, why did we take that to be zero, sir? Because in the next example, we didn't consider it to be zero.
here,
Sir,
okay, okay, okay. Let's do this. Here, what do you find out? What are we going to find out in this case? In this case, what are you finding out?
resistor across CL, uh, equivalent resistance
Resistance
across
across
CL.
CL, right? So where
Yeah.
do you apply test voltage in this case?
Across CL.
Right? Like this, right?
Yes, yes.
Correct? Now, if you apply a test voltage here,
Correct.
can you get any voltage VGS here?
No, sir, because it's open circuit.
Here, there is no connection, right? There is no connection between
Yes,
this and this, right? So you're not
yes.
going to get any resistance there, right? Oh, sorry, any value of VGS there. Fine. So if
Okay, okay,
VGS
sir.
is equal to
Okay,
0,
sir.
then GM VGS is also going to be 0, right?
Okay, sir. Okay, sir.
However, that is not going to be the case here, in this case, because
Yeah,
here you
that
are
I
actually,
understood, sir.
fine, fine, yes.
Thank you, sir.
So,
So here one quick question, right?
uh,
Maybe instead of considering that V test as unknown, maybe we can apply one node so that equations will become easier, right?
yeah, it's up to you, doesn't matter, whatever
Okay.
suits you, whatever suits
Because
you.
okay, we are increasing number of variables, so that's what I want to understand.
Yeah, yeah, it's up to you, it's totally up to you, it's whatever suits you. I find it convenient like this because it is then easy for me to keep track. Okay,
Okay, yeah.
fine.
So in my direction, maybe if we find the current in the circuit and inverse that, we'll get that
Yeah,
R
yeah,
value.
it's all up to you. I mean, whatever you find best. So positive feedback. I mean, feedback you understood, right? I also talked about it in the very first tutorial. So feedback, I guess everyone knows and understood feedback,
Yes,
the
yes,
concept, right?
yes.
Yes, sir.
Effects of
Yes, sir.
feedback. Also, I think probably you understood effects of feedback.
यस सर उसमें सर ने एक वीडियो स्पेशली बनाया था टीचर्स डे
हाँ
के लिए
हाँ. So I guess everyone understood all of this. So let's probably solve some questions. Now
Only
I
thing
hope
is,
yes.
uh, only thing is when we have both positive and negative feedbacks together, right? Those kind of problems.
What is the problem?
I mean, in that case, how
That
can we say?
okay, that is not going to come to you now. Okay,
Okay,
probably see. I will discuss actually a question like that in the maybe in the last session or probably in the session after that if we have a time, if we have some time.
okay,
If I
okay,
take some extra class, I will discuss some of these things which you have, which doubts you have. Okay. Fine. So this actually I covered today. The whole derivation I did for this. So I hope you don't find any issues with this. I hope you will be able to solve this question because I did the whole derivation here. Just have to put values and all. Okay. By the way, you just cross check on your own also. I might have made some mistakes. It is probable, right? I am doing here. I am very, my accuracy is very bad. So I might have made some mistake while deriving this. So just cross check on your own. Otherwise, don't blame me afterwards that sir you made this, you wrote it here and it is wrong. I make mistakes often. Okay, so it's up to you to just I mean verify this whether this is correct or not. Did I make any calculation mistake somewhere or not? Okay, verify this.
Yes,
All
sir.
right. So after if that is not a problem, then let's. Huh. This is a very easy question. Just to show confidence. Tell me. So T of S is a transfer function here, okay, and it is given by this. It is given here. So the question is, what is the second order approximation of T of S using dominant pole concept? That is the question here.
So can I tell the answer?
Yeah, tell the answer.
Yeah, s square plus 2s plus 1.
0.25.
Yeah, how do you find out? Find it. Find it.
Sir, we have to first calculate the gain of this transfer function,
Why gain? Why gain?
so that the original transfer function and the approximated transfer function have the same gain.
Okay, that is good. Yes. So yeah, tell me something. What uh, actually
Maybe
correct? Yes. So what is the gain of this transfer function?
1.
Is
1
it?
10 divided by 1.25, right?
8 into 1.25.
Yes. So it is 1. Yes.
Only for s as s tends to 0, as we are
Yes.
going for the dominant pole concept.
Yes. Yes. Exactly. Exactly. Yes. So the gain here is 1, right? And as one of you correctly pointed out, the gain because we are making an approximation here of the original transfer function, the DC characteristic shouldn't change, right? Because this is a low pass kind of a response, isn't it? And we are making a dominant pole approximation. You see, this is probably how it is. Okay. So if we are making an approximation of this using dominant pole, we are probably ignoring the third pole. Okay, third pole which is somewhere here, we are going to ignore it. We are going to say that okay, it is probably like this only. Okay. So but in all the situation, the gain of the system shouldn't change, right? DC gain of the system shouldn't change. So that is why first we find out what is the DC gain of the system transfer function. So that is one, as you correctly pointed out. Yes. So what is the next thing that we should do? We have to find
So
out.
we
Poles
We have to find out poles, right? So what are the poles here?
-8. S is equal to -8. One pole.
-8. Yes. Other poles.
Complex poles will get it, looks like.
We have complex poles, right? So
Yeah.
what is the magnitude of those complex poles? So let's calculate the complex poles. So we have
My
-2 plus
plus
minus
and
root over 4
4 minus
minus
4 into 1.25
4 into 1.25 divided
divided
by
by
2,
2.
right? And what is this? -1 plus minus
We'll
root
have
over
minus
0.25, right? J 0.25, right?
Right, sir. Right.
Right.
Hmm. So what is the magnitude of this?
Square root of 1 square plus 0.25.
So it is 1 plus
0.25.
0.25 the whole square, right? No, sorry, only
No, no, only
0.25.
0.25.
Yes. So it is 1.25, right?
Yes,
So it
1.25.
is 1.25 under root. So and this will be what? Minus
1.11.
the magnitude is 1.25, right? And the magnitude of this is 8, right? So tell me something. Is 1.25 root of 1.25 much less than 8 or not?
Yes,
I mean,
Yes.
by much less than I want. Is it like 4 times or not?
yes, less than 4
Yes.
times.
Yeah, I mean it is definitely more than 4 times, right?
Yes, sir.
Correct. So that is why we can actually we can say that this 8 here is so big that it can be ignored, right? Compared to neglected compared to the other two poles, right? So probably this 8 is coming here. This is probably 8. This is probably 8 and the other two poles are probably here. Since it is a complex pole, the the plot will be something different, okay? As a complex pole, the plot will be slightly different. It will be slightly different, okay? It will suddenly start to drop like this. This will be slightly different here, but you get the idea, right? So the second order transfer function should be what kind of?
1
T of s
divided
should
by.
be 1 divided by 1, is
Yes,
it? 10 divided by
because
8, right?
DC gain we have found out as 1.
Yeah, we have found out DC gain, so let's see whether this is correct or not. Is this fine
Oh, yes, yes.
right now?
Yeah, in that case, why should we need to consider the DC gain?
uh, it is uh, it is to make sure that you do it correctly, because you see ultimately what I did is I found out what is the dominant pole. Okay, here actually it was very easy, so I directly wrote it like this, but there might be cases where you have to uh, actually write in that way only. Okay, you see here what I did was I found out what which pole is the non-dominant pole. Okay, I found it, and then what I did is, since it turned out to be s is equal to -8, what I did, where are we going to be if we are making an approximation, uh, second order approximation of the transfer function, we are mostly in which side of the we are mostly focusing on this side, right, before 8, right? Because before this magnitude response, before the frequency hits 8, only before that only we can approximate it, right? After that, that approximation might fail, isn't it?
Yes.
Yes. So we are in this side where the frequency is less than 8, right? We are in this side of the graph where the frequency is less than 8. So if the frequency is less than 8, I can simply neglect s compared to 8, right?
Yes.
So that is what I did. I mean, this is also another way to look at the same solution here.
Sir,
Yeah,
sir, what exactly do we mean by second order approximation?
it means that the overall transfer function is a second order. I mean, the wording of this question is slightly ambiguous, but this is what it meant.
Okay, sir.
Yeah. All right. So moving on.
Is it like we might be having a number of poles in the transfer function, and then we are reducing that to only 2 poles, kind of second order?
Uh, no. It's not like that. It is the wording is very. It is not very proper. Okay. It's not very properly worded. It's just it does just meant that you have to find out a second order transfer function which can approximate this overall transfer function. That's all.
I mean, in the second order, we'll be having two poles, right? So that
Yes.
is okay.
Yeah, so
Okay.
that's what. Yes. Yeah,
Okay.
second order is two poles. Yes.
So basically, we are trying to reduce the complexity of the system by finding out that second order.
Yeah, you can say that. Yes. This question. So what is this? Solve this question quickly. Amplifier has a DC gain of 1000 and upper 3 dB frequency of 500 kilohertz. Find its transfer function and gain bandwidth product. So DC gain is given to you 1000, and you also given gain bandwidth product. Oh, sorry, upper 3 dB frequency. That is 500 kilohertz. Oh. So tell me what will be the transfer function. First of all, so this is actually. Oh no, so you tell me what will be the transfer function.
Let's say it's a low pass filter. AU.
Okay, then what?
And then
1000 upon
Come
1
again.
plus s upon s by omega.
1000 upon 1 plus
1
s
plus
upon.
omega,
S by omega.
3 dB.
Okay, this is what you are saying. So tell me, is this when this answer is definitely what I intended? I mean, this question, the answer is definitely what I wanted to hear, but is the question properly framed?
No.
Right? It is not properly framed
So
because is I
it
have
is
just given a
not
DC
clear
gain here.
that
Yeah,
it is not clear that whether it is only low pass or it's band pass or high pass. We are just assuming that
yeah,
it might be
correct.
low pass.
Also, it has not mentioned how many poles are there in the system, right?
Yeah, which are the system we don't know.
Yes,
The
sir.
number of poles we don't know, right? Only one 3D frequency we know. But after 3D frequency, there can be a lot of poles, isn't it?
Yes, sir.
Yes.
So this is a very badly framed question. I just wanted to put it out there. Okay. Yeah, it's fine. I just wanted to get an idea whether you understood or not. Fine. Good. This question I want you to solve yourself. Okay. This question I want you to solve yourself. Since I have solved one question very properly, I mean that whole circuit I have solved very properly, right? I have found out KCL and KVL for that this big circuit here. Okay. So this circuit here, it is nothing but you have to just apply KCL and KVLs everywhere and to find out. And when you find it out, you solve this part also. When you solve this, you will come across a very interesting point. You will observe a very interesting thing here.
Looks
Okay.
like differential amplifier.
Yes, it is a differential amplifier, and let's see what happens. I mean, just solve this. Okay. When you solve this, you will observe a very interesting thing. I want you to tell me what is the interesting thing that you observed in the next session. Okay. So probably this is probably it for today. I'll meet you again next Tuesday. Okay, with some new topics, new things to discuss. All right.
Okay, sir.
Thank you. Thank you everyone for joining today.
Thank you, sir.
Yeah.
Thank you,
Thank
Sir,
you.
sir.
one last question I have.
Yeah. Go on. Yes.
Uh, we are eliminating that whichever the pole is away from the origin, right? Generally, so which is
Uh,
not significant in the system response, right?
I mean the pole which is if
Away,
we have
far
already
away.
hit one, I mean the pole that is far away from the first pole. Okay,
Mm,
those poles we are ignoring.
correct, correct. So
Hmm.
why are we ignoring that only? Those are also contributing to the body plate also, right?
Yeah, but I talked about this in fair detail, right?
Hmm.
Uh, I talked about it in fair detail.
Okay.
Did you join?
So,
Did you join late? Were you late in
yeah,
joining?
actually, I haven't joined your session. Maybe other session I have joined.
Oh, okay, no problem. I have talked about it in fair detail. Okay, you can
Okay.
go through the YouTube this thing YouTube. I will be uploading on
Which
YouTube
week, sir? Which week?
this week, week 3.
Oh, okay. Okay. I
Okay,
joined late. Okay. Yeah.
it's
Okay.
fine. It's fine. It's no problem. I will be uploading it anyway, so there you can see. Okay.
Okay. I had a question just because of the magnitude would be higher for the which is long away from the pole, right? So which will decrease the amplitude more compared to the near dominant pole.
So
So in time domain response, if we see e power minus j omega, right? So that
so
magnitude wise, e power minus 8t compared to e power minus 3t.
uh
So 8t will decay more compared to
yeah,
minus 3t.
correct, correct. Yes,
So, and we are calling that third one as dominant pole compared to eighth
yeah.
one.
Yeah, you
Because,
actually watched the lecture. This, this is actually what I explained today. Okay, you
okay,
watch the YouTube this thing. You will be able to get it.
okay,
And
okay,
the
okay.
thing is that here, since the one that is decaying faster is not
Hmm.
going to contribute any time after that, right? See, this will
Okay.
be basically the sum of all the poles, right? All the exponentials, isn't it?
Oh, okay.
Isn't it? So
So the
basically,
amplitude contribution is very less. Okay, I
yeah. So
understand.
that is why it's a dominant pole. Okay.
Oh, okay, I understand.
Yeah,
Thank you.
Atharv,
Thank you.
yeah, welcome. Atharv, you raised your hand.
Yes, sir. Sir, one request to you, sir. Would you upload this recording session as soon as possible?
Yeah, I will be uploading it now itself. Okay.
Okay, sir. Thank you, sir.
Yeah, welcome.
Thank you very much.
Yeah, welcome.